John serves as the Vice President of Design Technology and Automation at ARM. He has strategic responsibility for all aspects of CAD and EDA design methodology, and that includes both ARM's internal production and external IP deployment methodologies. John?
Yeah, I'm actually in disguise as well today. It's a management panel, so I've put my suit on as well. So I think that's the big difference about the panel today. Everyone has suits. Okay, here we go. Ta-da. Try another. Okay. So what's this really about? It's all about the money, and we make money by getting our devices into products. And today for us, the product reality is software first, then hardware. I like all the points that Gadi was making about productivity. Obviously, we make more money the more productive we are, and the faster we go through our design and development flows. So for us at ARM, really, we're about getting through that product development cycle ourselves and enabling our partners to build their products through concurrently supporting engineering with them. And critically, that's concurrently supporting both software engineering and the hardware engineering to get the SOCs out. I think you'll probably hear from all the panel as we go through. We've got a smorgasbord of use models for ESL. I think I'll just kind of highlight a couple of these, give a little bit of insight into the uses at ARM. We're very often trying to operate a very number of years ahead of the curve, trying to define new instruction set architectures, new platform architectures in anticipation of product requirements 5-10 years out. To do that, you need an awful lot of architectural exploration tools. And ESL at the correct abstraction levels are absolutely the foundation of a lot of what-if analysis to start defining instruction sets, to start defining new bus architectures, and to hopefully get the characteristics of those in terms of power, performance, right early on. And one of the points I want to make, and it relates to the productivity thing, people often think ESL is a panacea, and they'll go, we can do high-level synthesis, we can do accurate power modeling. It's a tool to help you through the design process, not something that's going to allow you to enter at an abstraction level, press a magic button, and get an answer out. I would love it if that happened. I'm worried that in 2020, 2025, we're going to have acres and acres of dark silicon that we've got to fill with designs to make money. It keeps me awake at night of how we're going to design those chips in a tractable time. But today, please focus on the practical reality. Use it to help you through the design process, not as a magic bullet. Again, we've talked about using this for software. There's various kinds of software development. There's getting all of your drivers and your firmware together before the silicon comes back. There's supporting the application development community ahead not only of the silicon, but ahead of the product. And that's a very important area when you're trying out new concepts in instruction architectures, new concepts in platform architecture. Key thing to make all this happen is to have interoperability for models. Everything needs to plug together at a model level, because otherwise you cannot build a representation of your future or your emerging platforms. And the challenge we have is that everyone also has legacy. I'm not just able to greenfield and write a completely new model in the syntax and grammar that's my favorite religion today. I'm always going to have to integrate some legacy models, some legacy verification IP, a legacy algorithm, or a new algorithm that's not conceived. So my appeal to the ESL community is stop having religion about one way to do it. Think interoperability, think legacy first. And also, we see this a lot in ARM. It's not just what we want to do. Whatever it is that we do, we define a new platform, we define a new architectures for our next generation multiprocessor platforms. People will want to extend it, right? Improving time to product is about letting people diversify. in order to do that, every interoperability framework around ESL needs to be extensible. It needs to incorporate legacy, and it needs to be extensible. We've had some good progress over the last couple of years, and this is a kind of an illustration of this is where ESL is practically for us today. We are able, through interoperability standards like the OSCE TLM, to ship models of our ARM cores, both the ones that exist today and the ones that are coming down the pipe, into a variety of EDA frameworks. And at a basic model interoperability level, you can plug things together. But then when you get on to using these models and using them for things that you need to find out about your design, so maybe I want to debug performance on my bus. Maybe I want to debug why has the software failed? Is it a deadlock in a bus system? Is it a deadlock in a processor? I'm doing some validation. Or maybe I want to figure out, is the power profile that I expected for this part converging or diverging? There's an awful lot of detail required beyond those basic interoperability mechanisms to actually make true interoperable and usable systems. So we see continual challenges with these modeling paradigms today to get us to that next level of being able to plug the legacy together with the future and to use it to practically accelerate design.